Not all the classes today got through everything that we needed to get through, and consequently, I think a bunch of you are going to struggle tonight. So I thought I'd do a couple of problems to try to help you out, maybe clarify some things, or at least get you more prepared to ask questions tomorrow. So, number 15, we're supposed to write this thing as a definite integral, but before we do that, I'm hoping I can explain what things mean. So the limit out front, we're going to tackle that last. We'll do this sigma thing here in the middle. So this is read as the sum from I equals 1 to n of e to the power u sub I plus 2 times delta x sub I. We're going to write out a few terms because this sum means we're going to add a bunch of things together. We're going to use I equals 1 and I equals 2 and I equals 3. The last term would be I equals n. So the first term, we'll put a 1 where these i's are, and that would be e to the power u sub 1 plus 2 multiplied by delta x sub 1. Okay? Oh no, lost my piece. Okay. And then the next term we will use I equals 2. So that would be e to the power u sub 2. Still plus 2. We're just putting in i's, or 2's where the i's are, and delta x sub 2. Using I equals 3, that would be e to the power u sub 3 plus 2. And multiplied by delta x sub 3, we'll just write one more in another color. Using I equals 4, e to the power u sub 4 plus 2, of course, times delta x sub 4. Now this is going to continue on until we substitute in n, which is going to be e to the power u sub n plus 2 delta x sub n. And the structure I want you to see is height times width, height times width, height times width, height times width. We're adding up a bunch of rectangles, heights and widths. We're finding an area under a curve. Between 0 and 2, do you know what graph is being referred to by this e to the power u sub I plus 2 stuff? That's the graph y equals e to the power x plus 2. We're talking about this region 0 to 2 because we're given a Riemann sum. The widths of the rectangles aren't necessarily uniforms and their heights aren't necessarily found in the same place. So this red rectangle is just the first rectangle. Delta x sub 1 is the width of this rectangle, and u sub 1, I didn't leave myself enough room, is some x value where that height is found. So whatever u sub 1 is, we put it into e to the x plus 2, which is how we got this height. And this next rectangle has a width of delta x sub 2. And somewhere on that interval is some place called u sub 2. That number was put into e to the x plus 2, and we got this height. So we were told to write a definite integral, and I don't think that's hard, but we still haven't figured out what this limit out front means. Well, that says the limit and the maximum delta x sub I approaches 0. Well, we know what 0 means, and this is telling us a delta x approaches 0. So what would that mean? Let's say for this orange box. Can I get, oh, I totally got it. Okay, so the maximum size of this delta x sub or I'm sorry, yeah, this delta x sub 2 goes to 0, what would that mean for this thing to go to 0, that width to go to 0? It would mean we would have a very skinny rectangle that would be almost 0 units wide. I lost my x-axis. That would be what happens when the delta x's go to 0. But notice, that's all the delta x's. Delta x sub 1, delta x sub 2, delta x sub 3, and so on down the line. Ooh, put the I back. So this thing's going to be almost 0. This thing's going to be almost 0. This width will be 0. This width will be 0. How many rectangles would we need to draw in to fill up the area underneath e to the x plus 2 on the interval 0 to 2? Oh man, 0's in the wrong place. I'm sure you were yelling at me earlier. Well, let's think about it. The width of the first rectangle is basically 0, and the width of the second rectangle is basically 0, and the width of the third rectangle is basically 0. So we're going to need a whole bunch of very skinny rectangles. Turns out we'll need infinitely many rectangles. So that's exactly the same as saying the limit as the number of rectangles goes to infinity. It's just a different form. So what does that mean? Well, the exact area under e to the x plus 2 on 0, 2 was what we were trying to write. We were trying to write the definite integral from 0 to 2 of e to the x plus 2 times dx. I think the 0 and 2 are obvious. Those are the lower and upper bounds of integration where we're finding area. E to the x plus 2 was a little hard to figure out, but that is what was going on for the heights of each rectangle. Where did dx come from? Well, dx is an infinitesimal, a very small width, and that came from all of these delta x's. Each of these areas is width times height, width times height, width times height. The dx is an infinitesimally small width when we're talking about infinitely many rectangles in a finite area. You're supposed to evaluate the definite integral from -3 to 4 of e dx, and I thought if you drew a sketch, that would give you all the information, I suppose. Maybe, maybe not. So what function are we talking about? We're talking about the function, the horizontal line, y equals e. Definite integrals find area under a curve. So we're trying to find the area underneath y equals e in between -3 and 4. Okay. So eventually you'll be able to use your calculator for this, but e is a horizontal line. We actually have the area of a rectangle that we're trying to find. This is going to be a width of 4 minus -3 times the height of e. That's just 7 times e. Let's do that again with some more normal looking numbers. What about the definite integral from -1 to 4 of 3 dx? This is asking for the area under a particular curve, y equals 3, in between -1 and 4. We want this area. You notice again, this is another easy problem. We're finding the area of a rectangle. That area is 4 minus -1, or 5, a width of 5, times a height of 3, which is just going to be 15.